Hi, now I will explain my assignment 5. The first, of course, we will import all needed libraries and set the pipeline and load in our data, simple data, information about our data, null values, and drop the null values and show the descriptive statistics with the describe. And here we can see the correlation matrix, the variances, and the shape and data range from the 2013 to 2017. And this is the distribution of our features, mean temperature, humidity, and wind speed, and mean pressure. Here the MODA is 30, and here is 70. Time series analysis. First, I visualize the time series, trends, seasonality, and patterns, and the decomposition with the periods 365. This is the trend, seasonality, and residual. And we here split our data to train and test. 80 is for training, 20 is for testing. Our target column is mean temperature. Here, exponential smoothing. Here, I assume an additive trend and additive seasonality with a yearly period of 365 days, because the data is daily and we clearly see yearly temperature cycles. After fitting here, I forecast the next endpoints, where n is exactly the length of the test set. To make the visualization smoother and easier to read, I apply a 7-day rolling mean, pause to the train, the test, and the forecast. Here we can see our result, smoothed. Green is our forecast of our model. Orange is test. And here we can see the not bad results, not such big differentials. And in my case, MSE is about 6.25. It is mean absolute error is about 1.95. So an average HGS model makes an absolute error or less than 2 degrees Celsius, which is quite reasonable for a real climate data. And next is naive forecasting methods. To understand if 2 degree is good, I compare ETS with two very simple and naive baselines. The first baseline predicts the constant value, just the last temperature from the training set for all future days. The second baseline is yesterday equals today. For each test day, I predict the value from the previous day. Then I compute the same metrics for both baselines. The constant baseline is very bad. Its MSE is around 79 and MAE around 8 degrees. The yesterday baseline is much stronger, with MSE roughly 2.84 and MAE about 1.26. So ETS is clearly better than the stupid constant forecast, but in this dataset, it is worse than the very strong yesterday baseline, which already captures a lot of short-term structure in the data. This is an important observation. A more complex model is not always better than a simple baseline. So next is ARIMA and SARIMAX model. Next, I experiment with an ARIMA SARIMAX model. I start with order 2, 1, 2, which means two auto-regressive terms. One is first order differencing, and two moving average terms. On the plot with and here we fit it and forecast. On the plot with train, test, and ARIMA forecast, we can see that the model really follows the general level, but it doesn't capture the detailed oscillation as nicely. And here I show the same thing, but smooth to better visual. M squared error is about 66, and m squared absolute error is 7. So in this configuration, ARIMA is much worse than ETS and even worse than the post-knife baselines. In a real project, I will tune the ARIMA orders or add a seasonal component, but for the assignment, it's enough to show one working ARIMA model and to compare its performance. And feature engineering for predictive analytics. Now I switch from pure time series models to more general supervised learning models, KNN and linear regression. First, I create additional features from the time series, like leg 1, leg 2, wellness 3, day of week, and months. Leg 1, leg 2, leg 3 are temperature 1, 2, and 3 days ago. Wellness 3 is a 3-day rolling mean of past temperatures. Day of week comes from the index and encodes the day of the week from 0 to 6. Months is the month number. I drop rows with missing values after shifting and then split into train and test again, still without shuffling. Here I get 1,167 training samples and 292 test samples, each with 6 features. And first is KNN regression and elbow method. For key nearest neighbors regression, I first run an elbow search over different values of key from 1 to 20. Here we can see the result. I wrap the model into a pipeline and with standard scaler, because KNN is distance based and works better when all features are on a similar scale. On the first plot, elbow method for KNN, I can see that the MSE decreases quickly when I go from 1 to about 4, and then it flattens. I show the R squared here, which increases and then also stabilizes. I select the best key as the one with minimal MSE is the here we choose minimum, and here we can see it's 18 because the minimum R squared is 18 here. Then I fit the final KNN model and evaluate it. So I report MSE, MAE, R squared as the accuracy metric for this regression model on the plots of actual versus predicted, and on the residual plots, we can see that KNN follows the true temperatures quite closely, and the residuals are relatively small and centered around 0. Here the scatter plot, and it's the just a graphic. Next, linear regression. In a similar way, I also trained a linear regression model using exactly the same feature set and the same train test split. I standardize the features, fit the regression, and then compute MSE, MAE, and R squared on the test set. And it's not differential from the KNN. They are somehow similar. It looks nicely. And here, their result with KNN and linear regression is not differently, I think. And it's simple prediction, simple data, true mean temperature, and the prediction of KNN and linear regression. Linear regression is better than the KNN here. Visualization and reporting. Visualization here, comparison of ETS, ARIMA, KNN, and linear regression with all graphics. Here I smoothed it to get better visual. And the residual error plots. It's the ETS residuals, ARIMA residuals, KNN residuals, and linear regression residuals. ARIMA make more errors than the ETS, but the best one is linear regression. And that's all.